Welcome to the multi-threaded asynchronous parallel world of Swift. I'm your host, Dion, and I'm really happy to be with you today. A little bit about myself. I've been doing iOS development since 2011, and I've been doing Swift development since day one. I've been building apps for watchOS, macOS, and Vapor, as well as the iPhone and iPad. And I currently run a company where I do contract development called BrightDigit. If you're interested in learning more about Swift development and enjoy this presentation, you might want to join me on my podcast, empower.apps.show. We're almost at 50 episodes, where we talk about a variety of topics such as choosing your backend, architecture, test-driven development, or backend technology such as Vapor, WebSockets, and more. So I highly recommend you check my podcast out. If you're interested in learning more about asynchronous development, I have a blog post on my Swift blog, learningswift.brightdigit.com, which you can check out. So what exactly am I going to be talking about today? Well, first we're going to talk about why this topic is important. Why is it important to learn about parallelism, concurrency, and asynchronous development? Where do we run into this problem? And what are some challenges when it comes to implementing this stuff? What has Apple provided in the past as far as APIs, as well as talking about promises and futures, and how third-party libraries and other components can help you do promises and futures within your application. No presentation is complete right now without touching upon Combine and Swift UI. And then at the end, we'll be talking about the future of Swift and asynchronous development. So the next question is, why is this important? Well, if any of you have been building computers over the last 20 or 30 years, you probably have noticed a big difference. That is the speed of CPUs. Around the mid-2000s, the speeds kind of petered off or stopped at around the 4 gigahertz mark. The problem ends up being, as more electronics are miniaturized and inserted into processors, there's a sort of thermal limitation that can be reached, and processor speed has to be decelerated in order to accommodate the high temperature within these mechanisms. So manufacturers, rather than trying to make CPU speed faster, started adding more cores. And as we can see, we have more and more cores in our CPUs today. This has relied on the operating system to be able to manage multiple jobs at the same time. And it's important as software developers from everywhere from the watchOS, which can have as little as 2 cores, to developing on servers with multiple cores, or developing for an iMac or iMac Pro, that we take advantage of the hardware as is rather than locking up the entire system. And so that's why I think this topic is important, is how we can allow for different tasks to be taken on in the background without locking down our whole application. So the ways to do that are through parallelism and concurrency. And I want to explain the difference between these two things. So here's an example of a couple of tasks which are being taken place. We have a pink task and a blue task. One on 1 core and a couple here on 2 cores. We can see in the first one to the left, we have an example of what's called concurrency, where an application can split up its tasks in such a way that the operating system can schedule them interspersed. If we have multiple cores, this is where we could do something like parallelism, where one task is dedicated to one operating system and another task is dedicated to another core, and another task is dedicated to another core. We can mix both of these two, so they're not necessarily exclusive, to where we are both executing concurrency and parallelism at the same time. So this is one way an operating system can better optimize your application, and why having alternate tasks might be breaking things down into tasks might make your application a lot more smoother to run in the user interface. So the other thing to think about is asynchronous programming. This is where you have some heavy-duty tasks that can be better performed without blocking the whole entire application. For instance, you might have a heavy-duty machine learning application, large disk access, or even calls to the outside especially, where you're waiting on an execution to complete from someone else. So here's an example of a task where nothing is really being done in the middle. For instance, making a network call. So if you make a network call and you're waiting and waiting and waiting, rather than locking up your whole application, you can then just simply give the application what call to make when it's completed. And then the operating system can add another task within. So where do we currently run this in programming on Swift right now? Well, chiefly, like I said, is network calls or URL requests. Here's an example of me downloading some random markdown and giving it a callback to run when that data task is completed. This is probably done millions of times by many developers. We get back an optional data, an optional response, and an optional error, and then we do whatever we want with that data when we receive it. Another example is when we deal with observing notifications through Notification Center. So here's an example of where we're posting a notification when a data task is completed, and then we add an observer, which then takes in some sort of method or closure to do something with the notification once it's completed. So I think the last one I want to cover is timers. So we can take this even further with timers to where when that notification is posted that the download is completed, we then start a timer and then run a specific piece of code once that timer is then completed. So those are examples of where we can pass in functions or closures when a specific method is completed. In other words, running that method asynchronously rather than getting a return result back right away. But as many developers have probably seen before, we oftentimes can run into issues where we're updating the UI outside of what's called the main thread or main queue. This is another example of where we run into threading or different issues with parallelism and concurrency. So in this example, we have that timer set up to run, but we need to make sure that when the timer reaches the point at which we need to update the UI to change the label of the text, we then have to do that on the main queue or on the main dispatch queue. So then we specify that within our call. Otherwise, we run into issues when we run this where we get the nice little warning telling us that we can't update the UI outside of the main thread. So how do operating systems manage this kind of stuff? Let's talk about two ways: processes and threads. So a process is typically one application that runs within the operating system. Sometimes applications can have multiple processes, if you've noticed, such as like helper applications, but for the most part, each application has one process. However, each of these processes can then be split up into separate threads. One thread might be set up for listening for network requests. One thread might be set up for updating the user interface. One thread might be processing stuff in the background, whatever it may be. This allows a operating system to then execute concurrency or parallelism within the application. One issue that you can run into is what's called a race condition. Race conditions are instances where two threads are reading and writing from the same spot, but they might not necessarily end up being in sync. So for instance, here's an example of writing from 1 to 20 and two separate threads, where each thread is reading from the highest number and then writing the next number highest and storing that in some sort of global variable. What we run into is that when we get to around 10, we see that the next thread still sees the previous value. And so then we end up getting repeats of various numbers. So in order to get around this, we need to use something like a barrier. Barriers can be either a semaphore of some sort or a lock. In this case, we're using a dispatch semaphore, where we are waiting for that semaphore to give us access to read and write, and then signaling for each thread that that is done, and then the next thread can read on. This creates what's called an atomic operation, where the read and write is done in one instance, or like almost like one operation within the CPU. And this prevents the one thread from reading and writing while another thread is reading and writing, and it keeps your counter, for instance, or read-write operation within sync. This can slow down the multi-threading, but it does prevent errors from happening, which is probably even more important than speed. So let's talk a little bit about what Apple has provided in the past when it comes to dealing with concurrency and parallelism and asynchronous methods. We've all run into Grand Central Dispatch before. It is probably the leading abstraction when it comes to multi-threading, concurrency, and parallelism and all that. And chief amongst those classes is what's called the DispatchQueue. So let's we've probably run stuff on the main DispatchQueue, which I've shown earlier when you want to update the UI. But here's an example of creating your own DispatchQueue using global, and then basically writing numbers, counter of some sort here, where we have two separate counters, each writing a number increasing till 1000. And as you can see here, it's interspersing the global queue with the main queue as it's writing each of these numbers out. So this is really about the management of tasks. That's kind of what queues are. They're an abstraction of a thread, and they give a little bit more control over the operating system and how it manages these threads and how these tasks are completed. So in some cases, if you want to run something in the background, you may want to run it on a new queue that you've created yourself. And you can do that pretty easily using GCD. Another thing that I've used before is what's called a dispatch group. So let's say, for instance, you want to download multiple URLs, but you don't care what order they download. They could all be downloaded at the same time. This is where DispatchQueue or dispatch group would really be useful. This way, you're not like having a queue of each URL, but saying, here, download all these URLs in whatever order. And it can be done asynchronously without needing, you just need to know when all of them are done, not necessarily in what order. So in this case, we are downloading multiple markdown files. We create a dispatch group, and then we, for each time we start that process, we call enter, and then when we're done, we call leave. And then with a dispatch group, you can either call notify or wait, depending on if you want to wait on that dispatch queue asynchronously or synchronously, and it'll just let you know when all those downloads are completed without having to queue each one next in a serial fashion, so to speak. GCD does provide also barriers as well. As we have talked about, we talked about the dispatch semaphore earlier, but you can also define a barrier within a queue itself. So a classic example of this is like, let's say you want to download multiple things, but you want to make sure that that access to the array is not done in such a fashion where two appends are done at the same time. This is where a barrier, for instance, would be really useful. You just pass in a flag when you call your async on your dispatch queue, and you could also pass in an attribute to say that this queue can be run concurrently, and then that array or that sequence of or collection is then accessed with a barrier so that the queue doesn't necessarily step on itself when it tries to run multiple things at the same time. I think one thing I've really liked to use lately are promises and futures. If you've done C#, JavaScript, any other language, you've probably seen these before. And they are available in Swift, but unfortunately through other libraries or packages in order to really use them. What's nice about this, it avoids the issue of callback hell, really. So let's say you have an asynchronous call that makes within another asynchronous call. You're going to have brackets within brackets, and it's a mess. What promises and futures really do is it uses functional programming then, and it uses things like maps, reduces, flat map, etc. for converting the results of a promise asynchronously to other results that you might need in the future. So what you'll often see is some sort of method which converts the promise or future or asynchronous method result synchronously. You might have something where it's an asynchronous conversion where you have to make another asynchronous call. You also have some way to do error handling typically in one of these promises, a way to do collections. If you have kind of like what we had done with the dispatch group, you have an always. So for instance, if no matter if there's an error or not, you want to be able to run some sort of process or finish something regardless of whether there's an error state or not from that asynchronous call. And then there's also typically a way to recover. So convert that error into something that's then useful, that's actual data. So those are a few of the methods that you'll run into with a lot of these promise packages and libraries. So what I have in this example here is I'm going to be downloading posts from this JSON placeholder REST API using a Swift Playground. And then we're going to make some using different libraries, using different promises. We're then going to pull these posts and then maybe pulling out the author of that post asynchronously as well. So here's an example of a download. Just takes in an ID, it automatically forms the URL, calls a URL session data task, and then it decodes that JSON into one of our schema structs that we've created, and then returns that result asynchronously to the callback that's called completion here in the method. So let's take a look at our first library, which is going to be SwiftNIO and the newly released SwiftNIO version 2 and how they do futures. So SwiftNIO is used throughout a variety of server-side and networking applications, including Vapor 4. There's major changes from SwiftNIO version 1, and SwiftNIO requires what's called an event loop, which is kind of its own abstraction of a thread, similar to how a DispatchQueue would work. And in SwiftNIO's case, it's more frequently like a networking request or channel. Unfortunately, I didn't find SwiftNIO to really be suited for client applications. So if you're doing anything on iOS or macOS, the way to do it with like a playground is you end up saying how many threads you want in your application, which I find really messy. And even some of the folks from SwiftNIO really discourage use of SwiftNIO for futures, but nevertheless, I did want to show an example, especially if you dabble into anything server side. I think it's important to know. The main promise class or promise struct is called an event loop future. So that's what you'll end up seeing. So here's our conversion of our download method to using the event loop future return as opposed to using a callback. So in this case, we make a promise of whatever type we're using, could be a post or a user, and then we make that promise. And then we call our download method. And for our completion, we can use neopromise.completewith and then return the future result. So here's that code in depth a little bit more. So within the download call that we had set up earlier, our completion closure is complete with. That takes in that result type and will then return that future result. So then if we want to say, for instance, get the title once that operation is completed, we can then call map here. Excuse me. We can call map here, which then converts the post, takes the title property of the post and returns that and creates an event loop future string of that title. In this example here, we are taking it a step further and making another asynchronous call. In this case, we are downloading our post, and then we take that post and we download the author of that post using the user ID property of the post. This uses flat map because we're making another asynchronous call within there. And then we call map within the call to the user to convert that combination of user and post into a authored post, which gives us the author of the post itself to our website here. We can also flatten the calls to, if we have a collection, for instance, we want to download all 100 posts here. So 1 from 100, we call map. We then map each individual ID to its future download of that post. And then again, inside there, we get the title for each one of these 100 posts. And then we can call event loop future when all succeed in this case to then pass in that array of futures. And what it does is it flattens it and converts the array of futures into a future of an array of titles. There is also when all completed, if you want to run that instead. That's if you don't want to fail. If one fails, you just want to get all the results, regardless of whether they're errors or results. But in this case, we only want an error we want an error if any one of them fail. So in this case, we're getting back an array of string as opposed to an array of results in this case. You can also call and all succeed or and all complete if you don't need access to that future, or you don't need access to that future or promise. You can call those as well. So you can use map if you want to convert the value that you'll eventually receive synchronously. Use flat map then if you want to return another future, and rather than getting a future, you end up flattening it to a single future for whatever value. In this case, we're downloading the author of that post, and so we needed to call flat map in that case. And then when all succeed, we call that when we want to take an array of futures and flatten it into a future of an array for easier data processing. So we've taken our, in this case, we have an array of the authored posts. We have every author and every post. When we want that result, we then pass in, we call in when complete in this case, and we get back the result. And then we can either do, we take that result and we do, we print the error out, or in this case, we take each one of these authored posts and print out the title and the name of the author in our playground here. So SwiftNIO version 2 also has the idea of being able to catch throwing errors. So there's flat map throwing for when you want a synchronous call that could possibly throw an error. That's one catch. And then they have when failure if you want to catch an error, when complete for completion, regardless of failure. They also have always as well if you don't need access to the future itself. And then there is a recover method for converting an error into whatever value type it's supposed to be. So that covers SwiftNIO. I think SwiftNIO is really robust. There are some language clarifications that you're going to need. They're a little bit challenging. But I think if you're doing anything server-side, it's not that hard to get used to, and there's definitely a lot of help and documentation out there. So if you're doing anything client-side, the leading library that I've seen a lot of people use is Max Howell's Promise Kit. Promise Kit is pretty solid. It's used by a lot of applications, and it's been around for quite a while. So let's take a look at what we did with SwiftNIO 2 and do the same thing with Promise Kit. So in this case, we are creating a promise, which is the leading struct or library that's used, or structure class that's used by Promise Kit to encapsulate these promise or future objects. And the way it works is its constructor gives you a callback that takes in what's called a resolver. And then when that application, or excuse me, when your asynchronous call is completed, you simply call resolver.resolve in this case with the result of that asynchronous call. So in this case, all we have to do is say self.download with the ID and decoder. And then for our completion, we call resolver.resolve, which then takes the result of our download. Here is the code in a little bit more depth. So in this case, resolver.resolve takes the result of the download, and now we have a promise. So similar to SwiftNIO, if we want to do a synchronous conversion, we simply call map to get the title of each of these posts from our downloads. If we want to do an asynchronous map, where we want to convert something asynchronously, such as getting the author of a post, we call then. So then takes in a post, and then it we take the user ID and we download the user ID, and then call map to convert that user that we get into an authored post. Again, make another asynchronous call within our then, and then make a synchronous call to then convert that user into a authored post. Here's an example where we're flattening again. So in this case, we take every post from 1 to 100 and call promise download. And then we are then given an array of promises. In this case, we call when fulfilled, and we pass in our array of promises, and that will convert that then into a promise array of strings for each title. So the difference is that we still use map to convert each promise synchronously into a new value. We use then to convert each promise into a new promise that's asynchronous. You can use done at the end if you want to do something with the successful result. You can also use when for flattening any array into a promise of array. Lastly, here's an example of done being used when we want to deal with the result. There is also a catch if you want to catch an error. And there's finally, if regardless of whether it's an error state or not, you need to shut something down. Like for instance, in this case, finishing the execution of a playground page. So as far as error handling, there's catch to catch an error. Ensure if you want to do something regardless of the failure state, and then recover for converting any error into a promise value. So here is a little chart to hopefully help you out. Again, this gives you a comparison. You can see Google promises. You can use then for a sync map or for async. They all use then, except for SwiftNIO uses flat map for asynchronous calls. The reason you have the asterisk with map under SwiftNIO is because if you're going to throw an error, you need to use flat map throwing. There's also asterisks with when all succeeded, depending on if SwiftNIO differentiates between a slow fail or a fast fail, depending on if you want an array of results or you just want an array with the success type only. Always is also available in always in SwiftNIO as well, depending on if you want to return a promise again. There's when complete and always. We can see recover is used throughout all of them. And then SwiftNIO uses when failure instead of catch. So I think premises are really nice. I hope they become native. There is a future type in Combine, which we'll talk about in a little bit, but it isn't really used for that purpose. Otherwise, if you're doing something reactive, for instance, or let's say you have multiple things that are dependent on each other and you want to broadcast them out to multiple channels or multiple user interface controls, I think this is where Combine can be really powerful, especially with the way it does reactive programming. Reactive programming being the idea of reacting to a value change and changing a user interface. And this is where I think it becomes useful. The big structure or class or pattern that's used is the idea of subscribers and publishers. So a publisher will provide updates to data, either a success and a failure type typically. And then subscribers typically will listen to those updates of data. And oftentimes it could be a SwiftUI view, for instance. So here's an example of a view which has an observed object which pulls the title of a markdown file and then displays that title. So here's an observable object which we'll be using. In this case, we have a publisher set up for the title of the markdown file, and then we have some sort of method that pulls the title of the markdown file from the URL and creates a publisher for us. We have to store the assignment of that title into a cancelable. So that's why you have cancelable there in the initializer at the bottom. But I want to show you specifically this markdown title publisher method and how it works and how we create a publisher out of a URL. So first of all, luckily we have, excuse me, luckily we have a data task publisher built in, and we showed off notification sender and timers as well. So both of those have native publishers available to us without needing to do any sort of work as far as creating the publisher manually. So we create the data task publisher. We then call try_map, which then tries to convert the data over to a string, assuming that all succeeds. If it does succeed, all we have to do is pull the first line from our markdown file, and we can assume that's pretty much going to be the title. Otherwise, if there's an error, we just return null. And then we call compact map in order to filter out those null values. And then we call erase to any publisher in order to do type erasure and keep it kind of simple as far as the type, because you'll notice a lot of these generic types can get really complicated if you've done any Swift UI or Combine lately. So I think that while promises are really good and actually used probably more useful more of the time, Combine is really useful when you're doing any sort of multiple values or doing any sort of stream of data, and you need to, and it's focused really on the user interface of some sort and reactive focus. Unfortunately, Combine is only available on the latest OSs. So if you're okay with limiting it to iOS 13 or Catalina or watchOS 6, then this makes a lot of sense. Otherwise, you're kind of stuck in a lot of cases and might have to use a third-party Combine library instead. So we've talked about promises in Combine. What's really the future of Swift and asynchronous programming? Well, there's a couple of links in my presentation here where Chris Latner, the creator of Swift, really goes over what he sees as a vision of asynchronous programming. I highly recommend you check out the concurrency manifesto. But the two key components that he sees are the future of Swift and asynchronous programming is the idea of adding async and await, which we've seen a lot in a lot of languages, JavaScript, C#, etc. The idea of having syntactic sugar to a promise, so that way you don't have necessarily a promise type all the time, but rather similar to how throws and tries work. And what they did with errors, async and await would work the same way with promises. So instead of taking in, for instance, a completion handler, it will then have syntactic sugar to say it's asynchronous, and that it and by that it'll automatically know that it's really returning a promise and not necessarily that type. And then await for when you want to handle a promise and act upon it accordingly. So here's some examples here about processing image data that you can pull up on the manifesto, as well as this coroutine that Chris posted as well. The other component that's even, I find more complex, but something that Chris also sees as important, is the idea of actors. These are used a lot in like Pony or Go or Rust. And the idea is keeping data immutable within an actor. So for instance, an actor can only update data within there. And this really is about addressing the issue with like race conditions and read-write issues as well. And this would be syntactic sugar as well. So for instance, we create like an actor for a table model, and then within the main actor, we then update the table view. And this will ensure that that data cannot be updated outside of that actor. I see this as even more farther down the road than like async and await already are, but important nevertheless. So thank you again for joining me for this presentation. I hope what you get out of it is that take advantage of the hardware by separating things into individual tasks within your application, but avoid convoluted logic in favor of easy maintenance. You want to provide a faster UI experience over speedier logic for sure. That is, don't try to make your application as fast as possible if it locks down your UI, for instance. Use abstractions as much as possible. Avoid writing close to the metal. That way, for instance, don't write an NS thread. And allow the operating system to use dispatch queues or promises in whatever way it sees fit. Also, avoid callback hell as much as possible, using promises and futures when you can. And then if you're doing anything reactive and it uses one of the newer OSs, or you're doing something on the UI, that's where Combine is going to be a really great fit. So if you want to know more, you can check out my blog post at the URL here. It's also in the QR code in case you want to use that. If you have any questions for me, there's questions obviously after this presentation, but you can reach me on Twitter at LeoGDion, or you can email me or check out my blog, learningswift.brightdigit.com. Thank you again.